Look at the internal architecture of a modern software-defined vehicle. You are no longer managing discrete mechanical parts. You are routing continuous data flows across hundreds of electronic control units, overlapping sensor arrays, and external communication networks. To ensure this network does not fail, global regulators require engineering teams to simultaneously satisfy 4 distinct safety and security standards: ISO26262 for functional safety, 21434 for cybersecurity, 21448 for the safety of the intended functionality, and the new ISO 8800 for artificial intelligence. In most organizations, these regulations are treated as separate domains. Safety engineers, security analysts, and AI data scientists work in isolated toolchains, generating thousands of pages of independent documentation to prove compliance. Multiplying the immense complexity of vehicle software by 4 separate, disconnected regulatory checklists exceeds the processing capacity of any engineering organization. It forces a procedural bottleneck that delays deployment and fragments the system design. This bottleneck creates a dangerous industry practice known as checkbox compliance. Instead of letting risk analysis guide the system architecture, teams build the vehicle first and then scramble to retroactively generate audit paperwork to match the finished product. This split screen shows the inevitable result: drift. On the left, engineers update a system architecture block due to a test failure. On the right, the static traceability matrix in a disconnected spreadsheet fails to update. The connection breaks. The spreadsheet still reads as compliant, but it now describes a system that no longer exists. This drift actively masks physical design flaws from auditors until the system reaches the road and fails. True compliance cannot be a retroactive checklist. It must be a byproduct of internalizing your processes into a single, unified methodology, executed through a continuous digital thread. To see why siloed compliance fails, we have to look at how risk is traditionally assessed. Safety teams perform hazard analysis and risk assessments, while cybersecurity teams run threat analysis and risk assessments. They use different metrics, different tools, and different definitions of failure. Consider a functional safety scenario. A front-facing sensor fails. To ensure passenger safety, the safety team writes a requirement demanding that the central processor instantly override the steering control to execute a fail-safe maneuver. Now, look at the cybersecurity scenario for the exact same system. To prevent remote hackers from taking control of the vehicle, the security team writes a requirement demanding a total lockout of any external processor attempting to seize the steering hardware. This diagram shows what happens at the physical ECU level. The safety pipeline requires immediate steering access. The security pipeline blocks all steering access. Evaluating component failures independently from malicious hacking guarantees these contradictory constraints. The architecture deadlocks before a single line of code is written. The engineering solution to this deadlock is STPA-Safe. It is a control systems methodology designed specifically to merge these isolated safety and security pipelines into one framework. Instead of categorizing risks as either physical hardware breakages or external software hacks, STPA-Safe evaluates both as dynamic control flaws. It asks, under what conditions will this system execute an unsafe or unsecure action? By treating both physical failures and remote hacks as control flaws, the methodology maps them into a single loss scenario tree, as shown here. From this single tree, engineers extract one unified set of safety and security constraints. The system is designed from the beginning to understand that a fail-safe maneuver must be authenticated, and a security lockout must not block emergency interventions. This unified approach eliminates the duplication of analysis effort and prevents architectural conflicts before system design even begins. While STPA-Safe manages deterministic logic, modern vehicles rely heavily on the non-deterministic logic of AI algorithms. A perfectly functioning neural network can still make a fatal decision if it encounters an environment it wasn't trained for. To audit this, ISO 8800 requires engineers to expand the traditional V model with a dedicated lifecycle branch for AI datasets. The entire structure relies on this bottom node, the training dataset, the foundational data establishing the network's weights and biases. AI compliance relies on establishing a causal model chain. If the training dataset contains a specific requirement gap, for example, failing to include radar signatures for certain species of wild animals at night, that gap becomes a systemic vulnerability. When the vehicle encounters a specific triggering condition in the real world, like heavy rain, that environmental trigger combines with the training data gap. The result is an AI misclassification hazard, leading directly to a collision. The standard mandates tracing this causal chain from the training dataset, proving mitigation through validation, independent testing, production, and ongoing field monitoring. If your engineering teams cannot trace a specific data omission directly to a vehicle-level hazard, your AI safety is an assumption. It cannot be genuinely audited. Executing this unified methodology across hardware, software, and AI datasets is beyond the capabilities of document-based systems engineering. Manual traceability cannot survive the volume of data generated. Early attempts at model-based engineering using SysML v1 failed to solve this. Teams were trapped by vendor lock-in, relying on brittle plugins and manual file transfers that corrupted data between departments. The structural solution to this data problem is SysML version 2. It abandons the legacy UML-based framework in favor of a kernel modeling language designed specifically for the semantics of systems engineering. SysML v2's primary innovation is the integration of standardized REST APIs and native OSLC data linking. Instead of copying requirements, SysML v2 creates precise semantic links. If text in an external requirement tool changes, the central architecture block inherently knows. In this ecosystem, files are never exported, duplicated, or emailed. The data exists in one place, and multiple tools simply view and interact with it. This establishes a single authoritative source of truth. The safety team, the AI team, and the software developers are all observing and modifying the exact same digital structure simultaneously. SysML v2 effectively transforms the system model from a static schematic into an active, globally integrated data hub. By establishing this data hub, we achieve the operational reality of modeling as evidence. Consider the daily workflow. An engineer assigns a safety integrity level, an ASIL rating, and inputs a specific hardware failure rate directly into a SysML v2 steering component block. Because of the standardized API, specialized analysis software running in the background instantly detects these new attributes without requiring the engineer to initiate a transfer. The external tool pulls the data and immediately constructs complex fault tree analyses and failure mode reports automatically. If the architecture team modifies the system design, perhaps adding a redundant processor, they simply update the model. Instantly, the connected analysis tool recalculates failure probabilities system-wide. Safety metrics update with zero manual intervention. In this environment, engineers do not stop designing to prepare for audits. Their daily modeling tasks intrinsically generate real-time compliance evidence as a natural byproduct of their work. Connecting concept design, software logic, dataset lifecycles, and field monitoring into one uninterrupted data stream creates a complete digital thread. We can observe the power of this thread during a post-deployment crisis. Imagine field monitoring detects that a specific camera sensor loses fidelity when exposed to direct glare at a certain angle. Engineering immediately drafts a new requirement at the top of the chain to adjust the sensor's exposure threshold to mitigate this limitation. Watch the digital thread execute. The requirement updates. The pulse immediately travels down the network. The system architecture model flags the associated OI training dataset as invalid for that specific glare condition, and the linked software test script instantly drops into a failure state. This digital thread replaces manual cross-departmental impact analysis with automated traceability. The system identifies affected components and flags test failures the moment a requirement is modified, providing the engineering team with an immediate map of the necessary changes. For organizations operating on a unified digital thread, the traditional panic-driven audit preparation phase ceases to exist. The enterprise transitions to a permanent operational state of continuous audit readiness. When external regulators review the system, they are no longer handed static PDFs or disconnected traceability matrices that obscure the actual design logic. Instead, auditors log directly into a global aggregation dashboard or run automated queries against the SysML API. They can verify the structural integrity, trace AI dataset lifecycles, and confirm test coverage for the entire system in real time. Process internalization extracts compliance from the realm of bureaucratic paperwork and embeds it directly into the engineering workflow. It replaces retroactive verification with continuous validation, allowing engineers to focus completely on architecting safer, more resilient systems.